So I'm going to go through this the best I can. I'm going to really suggest that you guys kind of read the book as well. And, I'm going to really stick with the book a lot on this stuff. In fact, the pictures that you'll see are just like pictures on page 548 and 549. We're going to really break this thing down. We have 4 days to go through this section. And, there's only 50 some problems. So we're really going to take it one step at a time. This is a really big deal, differential equations, that is. And, so I suggest that you read the intro there on page 548. It talks about this logistic model. And, we've dealt with a lot of differential equation stuff already. And I'll kind of talk about that as we go. The main one that the book is talking about is this exponential growth, how that doesn't really make sense because you end up, exponential growth when you're talking about a population model doesn't necessarily make sense because eventually there's something called the carry capacity that says that actually, like there is a limit to how many of whatever you're talking about, whatever organism you're talking about can live. And so you can look at that. I suggest you read it. It's very interesting. But the point it's making is that a logistic model is a form of differential equations, and that's what we're talking about. And then it goes on in the chapter preview to talk about, it's differential equations are used on just about any kind of study that you can think of. So I want to go over some definitions and a couple example problems and kind of give you guys an idea of what actually a differential equation is. And so they talk about a differential equation is an equation that's involving an unknown function, and that's going to be important. They have it y, an unknown function y, and its derivatives. And, they talk about how we've dealt with this actually a lot when we start with velocity, for instance, and we go find the position function from the velocity function. All of those things are solving differential equations. And so the one thing that you want to keep in mind is that these are equations and we are looking for something unknown, just like in algebra. But the difference is, and something that ends up being a big deal here, is that our unknown in algebra is just some value, right? Some number usually. But in differential equations, the unknown is actually a function. And the book gives these 3 examples of differential equations. And then what we're going to do is start off kind of like we would in just basic algebra, where we show you that, you can plug your solution back into the original equation to verify it works. And that's kind of how we're going to start with this. So again, I really suggest that you read through this, and I'm going to just kind of go through what they're saying. And they take a look at the first function here, or the first differential equation A here, and they say, what happens if y equals the cosine of 4x, okay? And again, this is a differential equation because we have this function y. Remember that everything that we're talking about in a differential equation is a function. So we have this function y, and we have its second derivative here. So let's go ahead and figure out what the second derivative of this function that they gave us. They're saying y is cosine of 4x. So let's find the first derivative of y, which would be negative 4 sine of 4x. And then the second derivative would be negative 16 cosine of 4x. So if we go back and look at the equation A as it is, they say, okay, well, the second derivative of y, and so the second derivative of y, what we just found is negative 16 cosine of 4x plus 16 times what we're guessing at this point is the solution, is y, right, times cosine of 4x is equal to 0. And sure enough, right, these two terms will cancel each other out, and they are 0. And so what the book is saying is that, well, then that means that that is the solution to our differential equation. And that's simple enough, and basically that's all we're going to end up doing for this first group of problems. There's a couple other things going on, and we got to talk a little bit about our definitions here. So let me get rid of this. So the order of the first definition is the order of a differential equation, and they're defining that as the highest order that appears in the derivative for the equation. So right, this is a first order differential equation, as is this, right? dy dx and y prime, right? That's first order. And a would be a second order differential equation. The next definition that they talk about is linear differential equations. And I actually have a picture of that. Hold on. Okay, so I guess this picture also talks about first order and second order. Again, that's first order, and this is second order. But they also, these are also linear functions, and a and b are also linear functions, but c is not a linear function, differential function. Sorry, I forgot the word differential there. But the reason this one is not linear is because if we distribute it on this right-hand side, we'd have a y squared. Okay, and so just like linear is always basically meant to the first power, it's still going to kind of mean the same thing, right? So this one is nonlinear, linear, linear, and then these two are also linear because we don't have a squared term. So a couple more definitions that they're talking about before we can do some example problems are initial conditions, and we've actually dealt with this a lot. And think back to our acceleration, velocity, position functions. And if you remember right, we were depending on how far we were going. Like, so if we had like all three of those, and we went in both directions, right? We were able to do this with derivatives. By starting with the position function, taking the derivative and getting to the velocity, and taking the second derivative and getting to the acceleration. But and we could also go backwards and go acceleration, velocity, and position by doing integrals. And if you think about the integrals that we would, when you're taking that integral, that definite integral, you would have to always add c to the end. Okay, and then we would start thinking about, okay, we can solve this for c if we knew the initial position of the function that we were heading toward. Okay, and so that's the same idea. And so we've had initial conditions before. And then they talk about the initial value problem is if you have the same number of initial values as you do for the order. So, for instance, if we have a first order differential equation, we would need one initial value. If we had a second order differential equation, we would need two initial values. And that's where really, sometimes we were doing position and velocity, and so then we'd only need one initial value. And then other times we'd be doing position, velocity, and acceleration, and we need two initial values. So again, I'm really just going through what the book says and just kind of paraphrasing it for you. Hopefully that helps a little bit. I'm going to go ahead and jump ahead to the problems I want you guys to look at. And so we're going to look at number 8 here. Okay, and so all we're doing here in this first section, and I'm talking about 7 to 10, is just verifying solutions. Okay, and so the mechanics of this is very, very simple. But, I think it's important to realize that this is kind of going back to like basic algebra, right? When you first had an equation, you're always told to, at the end of your solution, go plug it in, make sure it works. That's the part that we're going to start with. We're saying that, in number 8 here, we're saying that, this is our differential equation, and this is what we are saying our solution is. So let's make sure that this solution actually satisfies our original differential equation. And, what you see here, and remember, one of the tough things to keep straight about this is that this is a variable that stands for a function. That's what we solved for over here, okay? And so this differential equation, you're solving for y, but you notice that there's a y prime. So the derivative of y is also part of this equation. So for us to check it, we need to actually start off by finding the derivative of y, and then we'll plug both of those in to this to see if we get 0 at the end. Okay, so remember your power rules and that. So right, we're taking derivatives, and so it's very straightforward, right, when we take the derivative. C is a constant, by the way. So negative 3c t to the negative fourth is the derivative of y. And now again, now that we have both of these pieces of information, let's just make sure that these things satisfy this equation. Again, we're saying this is the solution. So we would plug this back in. T times our derivative of y, so negative 3c t to the negative fourth, plus 3y, okay, and remember y is a function, and it's the solution up here in the corner that we're saying it is, so 3 times ct to the negative third equals 0, and then we're just simplifying, right? So this first term, we're just doing exponent rules, 3c t to the negative third now, plus 3c t to the negative third, and sure enough that equals 0. And so what that means is that this is the solution to this differential equation. So now I'm down in the next section, and it says verifying solutions of initial value problems. And really there's not any real difference between what we just did in number 8 and what we're going to do here in number 12. The difference is now we have this initial value, so we would it makes it an initial value problem now, and so we would be able to find a little bit more. But for our purposes right now, we're still just verifying that the solution is correct. And again, it's very important, I think, and the whole point of us going through this is that you understand what a solution is for differential equations. The solution is a function. Okay, and so, right, what all this stuff is saying is that, if this is our differential equation, we're saying, oh, we did all this work and we found it, and we found the answer to be this. Let's make sure that that's true, okay? And again, this is just what the initial value would be, and so it just makes it a little bit different than what we did before, but for the purposes of this section, it makes it like no difference. So again, we have this function y that we think is the solution to this differential equation. Notice that we have, I guess we should say that this is a first order differential equation because of this. So we do need to find the derivative of what we think our solution is first before we can plug it back in here. So then dt equals, right, 48, oh boy, let's try that again, 48 t to the fifth is what we're saying that our y primed is. So let's go ahead and plug this in to see if this solution y is correct. So then we say t times the derivative of y, 48 t to the fifth, minus, good grief, minus 6 times what we think our solution is. And we're wondering if that's going to give us the right answer here. So then what we have is 48 t to the sixth minus 48t to the 6th plus 18. And, you know, these two cancel out, and so then we have 18 equals 18, and sure enough, this is our solution to this initial value problem. And that's all we're going to do for right now. So, you know, again, like I said a second ago, the mechanics of this are really not that big a deal. We're just kind of taking some derivatives, plugging them in, doing a little bit of algebra, and saying, okay, sweet. So, you know, I really suggest that you read the first page there, the first couple pages, you know, listen to kind of what I said. I didn't really say anything different, but, you know, I think maybe it'll help you kind of grasp kind of what the whole idea of all of this is going to end up being. Again, a very powerful tool, shows up in a lot of different subjects. And so to highlight a couple really important things, right? You know, these differential equations are made up of functions and this function's derivatives. And so the unknown in these differential equations is going to be a function, okay? So very important to understand that. So go ahead and take a look at, let's just do, oh, well, I'll post it on Google Classroom, but it's just these first two sections. Ask some questions if you need to.